Two-dimensional materials are crystalline substances with a thickness of a few atoms or less. The most famous of the 2D materials is graphene, a single layer of carbon atoms called a monolayer, which is hundreds of times stronger than steel, conducts electricity better than copper, and is completely flexible. Beyond graphene, there exists a host of 2D materials with a wide range of different properties. One group, called transition metal dichalcogenides, and known as TMDs, combine the incredible thinness of graphene with exceptional semiconductor properties. Unlike graphene, a TMD monolayer is 3 atoms thick. Each sheet consists of a layer of transition metal atoms such as molybdenum or tungsten, between 2 planes of chalcogen atoms such as sulfur or selenium. TMD monolayers are direct band-gap semiconductors, meaning they strongly emit light when excited electrically or optically. But for thicker TMD sheets such as bilayers and trilayers, the band gap is indirect and the excellent luminescence properties are lost. So, to utilize light emission from TMDs, individual monolayers must be isolated from a bulk crystal. To do this, researchers at the University of Sheffield use a method known as mechanical exfoliation. Although atoms within an individual layer are strongly bonded to one another, adjacent sheets are bound together very weakly through the van der Waals interaction. By simply applying sticky tape to the crystal, this weak interlayer bonding can be broken and thin films of material can be removed from the crystal surface. By then applying this tape onto a substrate such as glass and slowly peeling it back off, interlayer bonding between layers within the thin films can be broken further and single monolayers can be transferred onto the surface. Assembling different 2D materials into vertical stacks, one layer at a time, creates new artificial materials called van der Waals heterostructures. By careful control of the sheet order within the heterostructure, the properties of each individual layer can be combined to produce optoelectronic devices with tailor-made properties. This allows the construction of electroluminescent devices for light-emitting applications. As well as photodetectors for optical imaging sensors and 2D material transistors for the basis of flexible computational elements. Combining these different electrical and optical elements based upon van der Waals heterostructures has incredible potential for the development of new flexible electronic devices that could revolutionize current technology.